is your 5 steps to the 5 from chapter 10. It's on thermodynamics and gases. This goes along with chapters 12 and parts of chapter 11 in your textbook. So this is something we looked at in, I believe, December and January. All right. Yeah, in fact, that was the thing right before optics. So key ideas of this, which are actually, again, I think pretty important. Behavior of molecules, so what happens on a molecular basis, lets us predict what's happening on a larger scale as well. Heat is one way that energy can be transferred. Work is another way. So heat is simply a transfer when objects have different amount or different temperatures through conduction, convection, and radiation. That seemed to be a question for a lot of people when they filled out their topic checks. So I need to make sure I talk about that. Ideal gas law connects a bunch of variables, gas molecules, pressure, temperature, and volume. That's the Puvnert formula, PV equals nRT. Kinetic theory explains how individual molecular motion can lead to properties on a larger scale. Temperature is an example of those. We also need to make sure we talk about things like the thermodynamic processes, such as adiabatic, isovolumetric, isobaric, isothermal. So first law of thermodynamics, it basically is this. Change in internal energy is equal to the heat transferred to the system plus the work done on the system. So if these are positive, that means things are coming in. If they're negative, that means things are going out. So the thing you have to be careful of here, work is easier to think about, I think, in that if a system is expanding, the idea like a balloon that's getting larger and larger, that means it's pushing out on the world around it, which means it's losing joules of energy. So when a system's expanding, work is always negative. When a system is contracting, work is always positive because the system is being compressed by the outside world. That takes a force applied inward, so energy is being transferred due to the work, force times distance, acting inward. This is a little bit tougher because you can have heat flow into a system or out of a system without a change in temperature. Oftentimes there is a change in temperature, but if you're expanding, say here, so you're losing joules due to work, and you have heat flowing in, say from a flame or a hot area, those could just equal out, meaning that your internal energy doesn't change. This is the quantity that's directly related to the temperature of the object. And you can see that up here. Unfortunately, this formula is not on your formula sheet. This formula is on your formula sheet, which is a bit annoying. So this is the one I find more useful. You may want to write that down since this year you can use whatever version of your formula sheet you want. So the first law of thermodynamics is you can't win. In other words, you can't get more energy out of a system than is put into a system. So it's basically conservation of energy. Second law of thermodynamics I talked about, and it's not in a formula here, is that you always lose, meaning that thermodynamic processes are always less than their ideal efficiency. So the maximum efficiency you could have at a given temperature is defined by the temperatures in a thermodynamic process. So if you have a contraction and expansion happening at certain temperatures, there is a finite maximum efficiency you can have. And second law of thermodynamics says that never really happens because there's always some loss due to friction and non-conservative properties. So you do want to make sure you understand how to interpret a PV diagram. You can determine using the ideal gas law and PV values, since PV equals nRT and internal energy is equal to 3/2 nRT. And the idea is that the internal energy is directly related with temperature. Work can be determined by the area under the graph. And that would be positive or negative depending on whether this is the graph or the volume's expanding or contracting. Heat can't be determined directly from the diagram, but rather from the first law of thermodynamics. We did some examples in class with that. I want to do some again during, say, maybe a Google Hangout. This is rate of heat transfer. We did a free response with that, which I think was actually fairly useful. It's from last year's AP exam. Hopefully you have that with you. If not, I'll be happy to get a PDF of it for you. Temperature tells us the speed of vibrations. So the thing about that that's a little bit different is that the speed of vibrations also tells us, basically it's related to the internal energy on average per molecule, but that also depends on the type of molecules you have. So for example, if you have something that's at say 300 Kelvin, which is close to room temperature, a small molecule will be moving much faster than a large molecule. So for example, hydrogen gas moving much faster than oxygen gas or carbon dioxide or water molecules or things like that. They can all be at the same temperature. They all have the same kinetic energy, but they would not be moving the same speed. The other thing, and this is really important because I noticed that a lot of people had this misconception earlier in the year, is that just because you have a certain temperature doesn't mean that all the molecules, even if they're the same type of molecule, are moving at the same speed. There's a range of speeds here. So you can see as objects get hotter, that spread out more simply because there's more room to spread out, because here this would be basically at absolute zero. So yeah, you could say that on average, an oxygen molecule would be going a certain speed to have this kinetic energy, but a lot of them are down here and a lot of them are up here. Same way for an oxygen molecule at a colder temperature, on average you could say that would be the energy that it would have, that represents the temperature, but a lot of them a little different. So really temperature relates to the average kinetic energy of molecules. It does not necessarily relate to any individual one. And so that really relates to the idea of entropy, which is the second law of thermodynamics, that you can't win. It's basically because with many hundreds of millions and billions and trillions of molecules, while you could have individual molecules above or below something like this, if you have a hot object coming in contact with a cold object and you have a bunch of molecules collide with each other, on average you're going to have far more energy transferred to the cold object because a far higher percentage of those molecules are moving faster. Could you have a cold object with a particular molecule that's moving faster than that in a hot object? Yeah. So look at this area in here. This area in here, there's a few molecules of this cold object that are moving faster than a few molecules of the hot object. But on average, far more of these are moving faster than these. And that's why on average, when you have a hot object come in contact with a cold object, any molecule will on average transfer energy from hot to cold, and as a system it will always have a heat flow or energy flow from hot to cold. So the molecules move in random directions, and I think they show that here pretty well. You can have some energy flow from cold to hot based on and I don't like the way this is drawn necessarily. It implies that you can have molecules with less energy transfer to those with more. That's not true, but you can have some of the molecules in this cold area have more energy than the ones they collide with. But the net effect is always this. And if you are in thermal equilibrium, the net effect, although there is energy being transferred back and forth, is zero. Heat is represented by this variable. Internal energy is the sum of all energies. It can be kinetic energy or potential energies. That really comes down more when we talk about electricity, because in electricity we can have charges that are moving, but also the position they have could affect, say, a potential energy of those charges. That we tend not to think about that as much with thermodynamics, although one of the reasons which we might want to think about that is with phase changes. So if you have something, say, water at 32 degrees Celsius, it could be a gas, it could be a liquid, it could be a solid. Well, if you have water molecules that are solid, which is ice, those are lower in energy than water molecules which are a liquid or a gas. Even though there's the same temperature, their condition is more organized, and so they have less energy. You should know that we are going to handle things in terms of Kelvin. So these talk about heat transfer. I'm going to attach about a 3 or 4 minute video. I looked at like a 9-minute Khan Academy video. I might attach that also. It seems a little bit long. But there's one that's about 3 or 4 minutes that I think is pretty good. So basically, this is by direct contact. So if, for example, your hand touches, say, the tabletop, go ahead and do that now, it probably feels cool to you because human is around 98 degrees Fahrenheit or 37 Celsius. Room temperature is a little over 20 degrees Celsius, or about 70 degrees Fahrenheit. So there's heat flowing from your body, from your hand, to the table. And it feels to you like the table is cool. Really what that is heat flow from your hand to the table. So conduction is with direct contact. They show like a fireplace poker here. If you put this in the fire, it gets hotter and hotter and hotter up here, and eventually it'll get hot and could burn your hands. Convection is energy transfer due to density differences, and it's due to the fact that like objects that are less dense tend to rise. So when things get hot, they tend to rise. They swirl around a lot. Lava lamps are a good example of this. Heat above a fire is a good example of this. The Earth's inside, where we've got plate tectonics, so we've got the mantle and things that are churning around due to hot heat produced by radioactive decay inside the Earth is another good example of convection. Also, water heating up in a pan on a stove would be another good example. One thing about conduction, though, the rate at which something conducts depends on the material, how thick it is, and how much area there is for it to transfer. So this goes back to this formula up here. So this is thermal conductivity, area, temperature difference, L, which is actually odd. It's the thickness of it, and I think that's because here delta T is time. So we've got 2 T's already. We really couldn't use T for thickness. So joules per second, which is the rate of heat transfer, depends on the material itself. It's got a constant. Cross-sectional area, so more area, the more heat can be transferred. The bigger the temperature difference, more heat transferred. The thicker the material, the slower the rate of transfer. And they talk about that over here. Convection, again, from one through another through energy through fluid flow. And a fluid could be a gas. Radiation is transfer of energy without direct contact. It's through electromagnetic waves. Could be infrared. Could be anything else. So an example of that is if you have a fire and you're sitting away from the fire, not above it, feeling the heat from convection, but if you're sitting to the side of it, you can still feel heat. Or if you go out on a sunny day, it feels warm. There's no matter in space. Well, the way that heat gets there is the sun produces all sorts of electromagnetic waves. Some of those are absorbed by your skin and your face, and therefore your face would feel warm. So this is actually kind of important for understanding what happens. I could see the AP coming up with something where you're asked about the kinetic theory of gases, not so much in terms of a proof or things like that, but understanding that really you're talking about a population of molecules. So this is kind of important. The molecules are pretty far apart, so they don't exert electrical or gravitational forces between them. So compared to the size of molecules, the distance between them is pretty far. And the collisions between them are elastic, so kinetic energy is not lost in them. And that's between molecule and molecule, or molecule and container. Now, with a container, that means that they would always go off and bounce off at the same speed as they come in, except that it would be at a different angle. But with the interaction between molecule and molecule, because they'd be both moving different speeds, that depends a little bit on elastic collisions, which says that the total kinetic energy before would equal the total kinetic energy after, and the momentum before would equal the momentum after. And that's a little bit more equation-y, and I don't think you'll have to do that. So this relates to temperature. Again, the idea is that kinetic energy of a molecule is related to its speed. Tired, it's Sunday night, and mass. So two gases at the same temperature. So basically, if I have something like this, if the average speed, if they're at the same temperature, this tells me that gas A is more massive because they're moving slower. Super important. Pressures in pascals, even though a lot of times you'll hear like our atmosphere is 100 kilopascals, volume in cubic meters, N moles of gas, R gas constant, T temperature, and that's in Kelvin. Generally, I haven't seen this. You do want to be able to think about how to rearrange things. So for example, if PV equals nRT, a lot of times you can use ratios to figure out what happens. They give an example of a problem here. So basically, if this is a fixed volume and then the temperature changes, then the pressure should change also. And you think, wow, 20 down to 0, the pressure goes from something down to nothing. Essentially what you could do is you can figure out that actually that's not true. You got to think about this as 293 Kelvin, 273 Kelvin. And the pressure would drop proportionally, which is somewhere around 7%. So this is kind of interesting here. We talked about that when we did the syringe lab. First law of thermodynamics here. We'll do some examples with that, so I'm going to skip over that. You do want to recognize how to do PV diagrams, and I think this is actually pretty important. So imagine a gas cylinder. When the gas expands, the piston moves up, work done by the gas. So that means the work done on the gas is negative because the system's expanding. When this is being compressed down, work is done on the gas as positive. PV diagrams are almost always, in fact, I've always seen them pressure on this side, volume on this side. And so if you were to get the slope of this graph, P times 1 over V would equal a constant, right? I think we had a free response with that also, so you may want to go back and look at that. We were trying to use that to get the slope of a graph, something like that, P versus 1 over V. Help us tell the number of moles in a container. So, which has the highest temperature? Well, this is actually pretty cool. So if you think about this, then P times V together would give you the higher the number, the higher the temperature. Which path would you take on this to get warmer or colder? So higher PV is higher temperature. So A, B, and C take you to a higher temperature. Lower, E, F, and G. These kind of hard because you're getting higher in volume but lower in pressure, but we don't know if those are changing in which particular way. Because normally when you have something that's an isothermal process, it curves like this, and it's hard to tell here which is decreasing more than the other. Here, if volume increases more than pressure is decreasing, you would have an increase in temperature. If it's the other way around, you'd have a decrease. I like this example of how to find work using PV diagram. So movement to the right is negative work. Why? Because the system's expanding, and that means you're pushing out, which means it's like you're pushing energy out. So you have the most work done here because you're looking at all this area down below. Here, less energy. Here, the least energy. So most negative work done from A to A prime. The areas we're going the other way, to the left, you'd have the most work done on the system from A prime to A. So that's important to talk about. That's also on your formula sheet, I believe. Yep, that's formula T4. No work done in these cases because there's no change in volume. This is actually a really good example of the area under the graph equaling the magnitude of the work. So if we do something like this and something like this, you're increasing here as you go from I to J. You're basically having work done by the system, or negative work done on the system is expanding. And because that's done at a higher pressure temperature situation or line than you would have here, you would actually have more work done on the outside world by the system on line 1 than line 2. You end up at the same pressure and temperature here, whether no matter which path you take, but you do more work on the outside world using path 1. So path 1's area beneath it is all this. Path 2's area beneath it is only this. So we can figure out from here our initial conditions and here our final condition. We could figure out, if we know PV and the number of moles, we can figure out temperature and internal energy here and here. And if we know that, you might say, well, wait a minute, isn't it the same amount of work done? No, because there's heat that could also be transferred to or from the system. So notice they talk about that here. This I like. So we might end up, oh, that's kind of funny, answer keys on the same page. We might end up going over this during the week this week. And I have not looked at the answer to that, but that's kind of funny. I like this. So basically, if you're going around clockwise with something like this, then you're going to end up having a net work done by the system, which means work is leaving, but since you end up at the same place, that means net heat is coming in. This is what happens with traditional heat engines. If you're going counterclockwise like this, where you're basically decreasing in volume at a higher pressure, that's like a heat pump. They do a really good job of talking about that here. I got to move kind of fast, so we may end up just going through some of these things. I like this, I like this, I like this. And then there's some practice problems at the end. I'd honestly look through a lot of those and let me know what questions you have. I might actually have that as an assignment. So I think that's not a bad idea.